All right, so here's the big idea. We're trying to solve triangles. That means we're trying to find all the sides and we're trying to find all the angles. So this is about the law of sines, and it's really important to know when to use it. First, it's not a right triangle, right? So if it's a right triangle, you can use SOHCAHTOA, you can use inverse trig, you can use the Pythagorean theorem. This is when it's a triangle, an oblique triangle, where none of the angles is a right angle. And this came right from our textbook, right? This is important to pay attention to in terms of like what sides are labeled where. So we've got three angles. Notice that big angle B is opposite the lowercase b here. That is common, and that'll be standard when we're applying the law of sines. Okay. Other quick thing to make note of: all the angles add up to 180 degrees. That's an old concept. We know that. It's Euclidean geometry. There we go. Moving on. So the triangles we're talking about fit into one of four cases. Okay. In case one, we've been given two angles and a side. Essentially, that's these two. Okay. The order doesn't really matter because if you have two angles, you can solve for the third one really easily. So the side, we definitely need though in order to do this. If we just have angles, we can't solve for any of the sides. We definitely need a side in there. And then case two is we've got two sides that are right next to each other, and then the angle is not between those two sides. Okay. If the angle is between those two sides, it would be a side angle side triangle. Okay, that's case three. Case three is when you would use the law of cosines. And then case four is where you don't have any angles, you have only sides, right? So we're going to talk about case one and case two. That's when you use the law of sines. And this is the law of sines, all right? It's right here, because it's written all out. Now, you only use two of these statements together at once. So like sine A over A equals sine B over B. You wouldn't use all three all together. You can use two at a time, all right? And you're going to use that to solve triangles. So that's like the big idea. And then what you're going to look at is some background. So we're going to kind of rewind back, because what we need to be able to do is find angles too, which means we will need to do inverse trig. And that's what this next piece that you're about to see is all about before we dive into solving a triangle. Well, all right, so here's the background stuff. So we're really getting into it and trying to make sure you understand why certain things are happening. When we are finding angles inside of a triangle, we will need to use sine inverse because we're using the law of sines and we're looking for angles. So I'm rewinding back to sine inverse notes and reminding you that it only exists in quadrants 1 and 4, and the answer to a sine inverse function is actually an angle. That angle has to be between negative 90 degrees and 90 degrees, all right? So in order to explain why this matters, we're going to look at a trigonometric equation. This one is sine of theta equals 1/2. So to solve this, I could use the unit circle. What angles can I plug in here so that sine of that angle is 1/2? 1/2's on the unit circle. It's a y coordinate out here. And I'm actually going to put the answers in degrees because that's what we're going to be using when we're solving triangles here. So on the unit circle, that's 30 degrees. And then there's another one over here in quadrant 2. Now, I'm not actually using sine inverse right now, so I can actually look in any quadrant. 150 degrees is the other one that works. And I'm actually just going to list those two. I know that says all the solutions I just really want the ones that are between 0 and 360 degrees. When I do this for a triangle, it's going to be the ones between 0 and 180. Why 180? Because there's 180 degrees. That's the sum of the interior angles of a triangle, right, in Euclidean geometry. So how does this connect to sine inverse? Well, if I tried to solve this equation using inverse trig, I would have to do sine inverse, right? The answer would be our theta of 1/2. Sine inverse of 1/2 is our angle. So if I do that in the calculator, and that's why I'm doing this whole thing, sine inverse of 1/2, sine inverse of 1/2, third time's the charm, is 30 degrees according to our calculator, right? So we get 30 degrees here, all right? How do I get the 150? Our calculator doesn't show that. We can dive even deeper as to how the sine inverse function came to be, but it only gives us one answer, which is good, makes it a function, but it doesn't help us to get the 150 degrees. The only reason I knew it was that is because I had it on the unit circle. So that becomes a problem when I do problems like this, right? Sine of theta equals 0.67. How do I solve that problem without looking on the unit circle, right? It's not on the unit circle. So I'd have to do sine inverse of 0.67 to figure out which angle it is. And when I do sine inverse, by the way, to do that you have to hit the second button, then the sine button, then you can type in 0.67. Your answer is going to be 42.07 degrees. And if I want the other one, I got to find a way to figure that out. Here's how you figure it out. I'm going to draw a little picture to demonstrate this. Just drawing the first quadrant here. I'm going to try to zoom in to make sure you can see it. First quadrant and second quadrant. So if I've got 42 degrees, that's about like this. All right, I'm just going to label it as theta. That theta is 42 degrees approximately. Well, the y-coordinate on there, right, the y-coordinate on there is going to be identical to the y-coordinate that's over here, right? The x-coordinate I don't know, but the y-coordinate is going to be identical, the same height, right? So straight across. So what we're trying to do is we're trying to figure out what's the obtuse angle that matches that identical y-coordinate. In this case would be 0.67, right? What is the angle from 0 past that 42 degrees all the way over to here, right? What is that if I keep going past it? It's past 90. Well, the way you would figure that out is this theta here would match this theta over here, right? So you would just do 180 degrees minus theta to get that obtuse angle. And that actually kind of makes sense because if we did 180 minus 30 degrees, we'd get 150. So point being, when you have a problem like this and you're asked to find the angles, we know that there's more than one, right? There's actually an infinite number. We're going to use the ones that are between 0 and 180. So we do sine inverse in our calculator, we get this one, and then we have to get the other one by saying, what's 180 degrees minus 42.07? 180 minus 42.07 is 137.93 degrees, okay? So that'll get us both, and that will come in handy when we're applying this, when we're doing the law of sines in other problems, okay? So if you wanted to continue on with this warm-up, basically doing the same thing, okay, we've got a couple other ones down here. Now, this one, same exact idea. You would do sine inverse of that. You'd get your angle. You'd write it down. You'd do 180 minus it, and you get your other one. This one over here, okay, if you did sine inverse of 1.58, it's a trick question. And the reason I put that one there is because sometimes you'll be trying to solve a triangle and you'll realize this is an impossible triangle. So I'll give you some sides and angles, and you'll be trying to find for other sides and angles and realize, hey, this is impossible. This wouldn't actually make a triangle. And that'll happen in situations when you see like this, right? I can't do sine inverse of 1.58. And that's because the sine function only exists between -1 and 1, right? If you looked up here, the lowest sine goes is -1. The smallest y-coordinate is -1. The highest one, the biggest one is +1. So problems like this, there's no solution. No solution here. All right, and then this very last one is you'll get 2 solutions there. Okay, so you're going to use this when you go and you solve for angles in a triangle. Okay, so now we're going to actually solve a triangle. Finally, we've learned the background. So we're going to apply the law of sines in this particular problem. And the reason we're going to do that is first because it's not a right triangle, right? There's no 90-degree angle in here as far as we could tell, unless that one was 90, but we're going to see here that that is, in fact, not 90 degrees. The other reason we're doing that is because it's an angle-side-angle triangle, meaning I have 2 angles and 1 side, right? It's one of those case 1 triangles. So we're going to set up the law of sines, and here's how you do it. First, we're going to write sine of an angle over top of the opposite side equals the sine of an angle over the opposite side, right? So we can use 35 and A, 15 and B, and whatever C is and 5, right? Probably the easiest step is to find C right away, right? Finding C is pretty easy because you just need to do 180 degrees minus these two. So 180 minus 35 minus 15 is angle C. So we can actually just put that right up top or over here, I guess. C equals 130 degrees, right? 130 plus 35 plus 15 is 180 degrees. Perfect. So now if I wanted to use C, I could do 130 over 5, right? Equals some other ratio where I'm I'm looking for a particular side. So I've got 35, I'm going to use that, and that's across from an unknown side, A. And I can now solve for A from this setup. So this is, remember I said just use 2 at a time. This is 2 of those pieces of the law of sines, and I'm going to solve for A. And in order to do that, I'm going to have to multiply both sides times A, right? And then I'm going to have to multiply both sides times 5 at the same time, right? So if I multiply both sides times 5 over here as well, I'm going to end up with A times the sine of 130 equals 5 times the sine of 35. And I was just multiplying times 5 to cancel out these denominators. And then I'm dividing both sides by the sine of 130, right? Just basic algebra stuff. And when you do that, you're going to get an approximate answer. So 5 times the sine of 35, all right, divided by the sine of 130 degrees, that's going to give us about 3.74. And I don't have any units, so I'm just going to leave it like that. That's approximately what I'm going to get, 3.74 from rounding to 2 decimal places, okay? So that's the basic math on that. When you have it set up like this, to get rid of a denominator of A, you got to multiply both sides times A. So the A ends up over here. I multiplied both sides times 5. So 5 times the sine of 35 was here. And then the last step is to divide by that sine of 130. And those same steps happen every single time, right? So if I wanted to solve for this last side B, right, I'm going to set up the law of sines the exact same way. It'll be sine of, let's see, I can use 15 degrees over B equals the sine of, and I think I'll use 130 over 5 instead of using, what would that be, 35, because A was rounded, so I'm going to try to keep everything as exact as possible. Rather than using a rounded answer to find B, I'm going to use what I was originally given. So when I do all that, what I would do is the same exact steps. I'd multiply both sides times B, then I'd multiply both sides times 5, and then I'd have to be divided by the sine of 130. So when I do all of that, I get B to be approximately 1.69. And that's the 2 other sides that we were missing. So solving the triangle just meant solve for all the sides and all the angles. C was real easy because I had 2 angles, and I just needed to use the law of sines to find the sides. So that's sort of the easiest type of the law of sines. Next, we're going to do one where it's a little bit trickier. We have to think a little bit more. Here we go. Okay, this one's a little bit trickier, and that's because I'm only given 1 angle in here. In the previous problem, I had 2 angles. I could easily solve for the third. This one, I've only got 1 angle, but I do have 2 sides. So it's one of those case 2s, right? Sorry about the blurriness there. It's one of those case 2s where I have 2 sides and 1 angle, okay? So I'm going to set up the law of sines again. I'm going to do sine of something over its opposite side equals the sine of something, and that something is an angle, over the opposite side. Now, I don't really have much choice here because I can't have too much unknown here. I can only have one thing that I'm missing out of these 4 spots. So I know I have this angle 40 degrees, and that's across from a known side, 3. And then the only other known thing is this side here too. So it really eliminates my choice. I have to go with sine B over 2. And so here I'm solving for an angle, angle B. Okay? In order to solve for B, I got to basically isolate sine of B first. So I'd have to multiply both sides times 2, right? So I'd end up with 2 times the sine of 40 all over 3 equals the sine of B, right? I'd have to multiply both sides times 2. It would cancel here, end up with something like that. And you'd get the sine of B, if you plugged it in your calculator, and I guess we should make this approximation, it would be 0.4285, okay, approximately. So I used several decimal places there. Now, this goes right back to what we had done with that little warm-up, right? There are multiple angles that would satisfy this particular equation. I'm dealing in the context of a regular triangle here, so I know that there could be 1 or maybe 2 different cases because I only have one other restriction, and that is all 3 of them add up to 180 degrees, but I only have 1 so far. So I've got a lot to work with. This could be up to 140 degrees, right? So what we'll do is we'll do sine inverse of 0.4285, and we'll get we'll get our calculator to do that. Our calculator gives us an answer of 25.37 degrees. Okay, so that's so far so good. But remember that there's this other angle between 0 and 180 degrees that we can find. So we would do 180 minus this. And if you're wondering why I'm doing that, go rewind back to learn from that warm-up. So there's another angle. So B could either be 25.37 degrees, or it could be 180 minus that, which is 154.63 degrees. The thing is, and this is what you would do each time if you have sine of something equal, sine of an angle equals a number, you'd have to look at both of these answers. Now, 25.37 plus 40 is way less than 180, right? So that's a plausible answer. However, 154.63 degrees plus 40, we're already over 180 degrees. So you have to look at both of them and then evaluate if it could actually make sense. Remember, they can only add up to 180. So this one's impossible. This angle is not a possible solution for that angle. So you might be wondering, well, what if they both work? Well, if they both work, you basically create two optional triangles from there. So you would solve the whole problem with this one, which is what we're going to do in a second, and then you would go back, you'd double back, and you'd solve the whole thing again with this one, with that result, right? So you'd have two different possible triangles given these constraints, right? And that is a possibility in certain times. In this particular case, we had one solution, right? One triangle that it could possibly be. So we're going to use 25.37 to find the rest. So if B is 25.37, we can do 180 minus 40 and 25.37 to get C. And it turns out that that actually equals 114.63 degrees if you just subtract them. Okay? And now we have enough information to find side C. So we would do sine of 40 over 3 equals the sine of 114.63 degrees, of course, over C. And then it's the same exact steps that we had done in a previous problem. You do all that and you get 4.24 units of measure. Okay, it's a length. Okay, so now we've got side B, A, and C, and we've got all three angles. So we are all done solving for that triangle. Again, if this one worked, I'd have to go back and figure out what C would be based upon this solution. If it worked, let's say it was only 100 degrees. We'd say, hey, this is 100 degrees. So what's that one have to be? That one would have to be 40, because 40, 40, and 100 would make 180. So you'd have another whole problem. You'd have different answers for C, and you'd have another as an angle, and you'd have another answer for C as the side. All right? So it's a little tricky with that type for law of sines. It's this type and then the type I showed you the first time. Otherwise, we'll be using the law of cosines. Good luck.